Hello everyone. Today we're going to be looking at a question involving simultaneous equations. So the equations we're wanting to solve are up here. X plus 2z equals 1, 4x plus y plus 11z is equal to 4, and x plus 5y plus a squared times z plus equals a cubed plus a. A is a constant, and we don't know what it is. We're just going to leave it as some arbitrary constant for the moment. And the question is, for a given constant a, how many solutions are there of this particular problem? So usually, if we're presented with, for example, two simultaneous equations, there might be some ways we can fumble around to eventually find the solution. But when it comes to three simultaneous equations, fumbling might not help us. Surely we need a bit more of a consistent approach to actually solve these equations. The good news is that in x, y, and z, these particular equations are linear. We can see that x, y, and z only ever appear to the power of 1 and always appear by themselves. And so what that means is that we can use matrices to approach this problem. So what we're going to do is use matrices to actually solve this problem. So how does this go down? Well, I'm not going to explain the great details here, but the point of this solution is presented here with the key concepts. The idea is to express this system of equations as a matrix equation. A for some matrix A times U, some vector U, equals V for some vector V, and then we're going to use Gaussian elimination to determine how many solutions there are. In particular, what we're going to use is Gauss elimination to row reduce the matrix into row echelon form. Because once this is in row echelon form, we can actually easily read off how many solutions this particular problem has. All right, back to the problem at hand. X plus 2z is equal to 1, 4x plus y plus 11z is equal to 4, and x plus 5y plus a squared equals a cubed plus a. Let's try and write this in matrix form. The first equation is x plus 0y plus 2z is equal to 1. So we can put all of that information inside this matrix here. X appears with 1, y does not appear, and z appears with a 2. What about the next equation? 4x plus y plus 11z equals 4. Well, that information goes here. 4, 1, 11, and the 4 on the right-hand side goes over there. Finally, the last equation, x appears with a 1, 5y, that's a 5, and z, well, that's an a squared. And the a cubed plus a goes over there. So in matrix form, what we're trying to do is find how many solutions this particular problem has. Well, usually what we would want to do is set this up as an augmented matrix. So all that means is that we're going to put this matrix and this matrix together. So the 1, 4, and a cubed plus a goes here. Everything else, 1, 0, 2, 4, 1, 11, 1, 5, a squared. So what happens next? Well, we need to row reduce. Row reduce. How do we do that? Well, the point of row reduction is that we're going to add copies of one row to another row, hopefully to simplify this augmented matrix. In particular, what we want to do, since there's a 1 up here, we want to get rid of these numbers here. Somehow we want to make these 0. How can we do that to the second row? Well, since that's a 4 here and that's a 1 there, if we subtract 4 copies of the first row from the second row, we're going to end up with a 0 here. And that's pretty good. But it comes at a price. We have to do some work to work out what the new entries are. Well, 1 subtract 4 lots of 0, that's still just going to be 1. What about the next one? 11 minus 4 copies of 2, Well, 4 copies of 2 is 8, and 11 minus 8 is 3. 4 minus 4 copies of 1 is just 0. Finally, the last row, what can we do to that? Well, there's a 1 here, and there's a 1 here, so if we simply subtract the first row from the third row, we're going to end up with a 0 here, so that's pretty good. Row 3 minus row 1, 0, being 1 minus 1. 5 goes here, being 5 minus 0. And finally, a squared minus 2, that's just going to go down here. A squared minus 2. What about this one over here? A cubed plus a minus 1. Well, a cubed plus a minus 1. So we've got a couple of zeros here. That's pretty useful. But we're not done yet. Really, what we want this matrix here to be an upper triangular matrix, which means I somehow need to get rid of this entry as well. I need to get rid of this 5. Well, how can I do that? I can't subtract copies of row 1 because that'll make this entry non-zero. Instead, I'll try and use the second row. So I'll subtract 5 lots of the second row from the third row. So R3 is replaced with R3 minus 5 R2. So the first and second rows are going to stay the same. What about the third row? Well, 0 minus 5 lots of 0 is still 0. 5 minus 5 lots of 1 is 0. That was the whole point of this. And finally, a squared minus 2 minus 5 lots of 3. Well, 5 lots of 3 is 15. A squared minus 2 minus 15 is a squared minus 17. And finally, a cubed plus a minus 1 minus 5 lots of 0 is still a cubed plus a minus 1. We now actually have enough information to understand how many solutions this particular problem has, and it all boils down to this number a. In particular, whether or not a squared minus 17 is 0. If a squared minus 17 is not 0, then this matrix here is an upper triangular matrix and all of the diagonal entries are non-zero. And so that means that there is a unique solution of this particular problem. For this particular question, we don't actually need to work out what the solution is. If you wanted to do that, you would have to do some more Gaussian eliminations and eliminate these numbers here. But for the purposes of understanding how many solutions there are, leaving it at this form here is enough. So if a squared minus 17 is not 0, then there is a unique solution. But what happens if a squared minus 17 is 0? Well, it depends. It depends on whether this number over here is 0 as well. So what we notice is that if a squared minus 17 is 0, then that means, obviously, that a has to be equal to plus or minus the square root of 17. But if a is equal to plus or minus the square root of 17, you might be able to convince yourself that this number over here cannot be 0. A cubed plus a, well, no matter if a is plus root 17 or minus 17, that number is always going to be bigger than 1 in absolute value, and so subtracting 1 cannot give you 0, and so what that means is that it is impossible to have a cubed plus a minus 1 being equal to 0. But if this can't be 0 and this is 0, then there's no way to solve that equation. And so what that means is that there are, in fact, no solutions. So that was that particular problem there. This is an illustration of how useful matrices are in solving linear equations. We use matrices to set up the linear equation, and then we use Gaussian elimination, reduced it to row echelon form in order to find the number of solutions. It's this form here that is called row echelon form. And that is that.